Alright, this is the video What Just Happened. It says time is what prevents everything from happening at once, and that's by Albert Einstein. And this is particularly relevant because we're looking at the last kinematics motion equation, and this is the one that actually does not have time in it. So let's take a look at our learning goals, and we want students to be able to determine situations in which time is unavailable for measurement. Most of the time that's after the fact, or just in a situation in which you don't have a watch or something like that. Number two, we want you to be able to algebraically generate the last kinematics motion equation. We want you to be able to recognize relative motion, and you want to be able to use this, which is the last kinematics motion equation. So, frame of reference. If you sit still and then describe your motion, it seems pretty obvious that, hey, if I'm sitting still, I'm not moving. But that's not entirely the case. If you were to take a look at it from a different perspective, something along the lines of, hey, this is the Earth, and you're sitting perfectly still right there, but I'm observing you from over here. Even though you appear to be sitting perfectly still to yourself, to me it appears like you're moving in a circle. And we know that is Earth's rotation. That has to do with something called frames of reference. It turns out that motion is relative to the observer and the person who is in that reference frame. So you have to look at those sorts of things whenever you're analyzing motion. In other words, there's no such thing as absolute motion. So absolute motion, okay, does not exist. Okay, we can cross that off. If you look at it, it says many people say that the figure was motionless, but it's not. It's only motionless relative to the classroom or the Earth. If you were actually to see somebody on a spaceship or even somebody just going down the road beside you, to a person going down the road beside you, it would appear like the school is moving backwards and you're moving backwards with it. So motion is really dependent on the source and whoever's observing it. So one key thing is that we're going to use what's called Earth's inertial reference frame. So unless otherwise stated, all motion is observed from Earth. So just like the example we gave, the example would be you're sitting still because we're measuring it from Earth's perspective. So frames of reference can be particularly useful when we look at cars. You may be familiar with the idea of a rear-end collision and a head-on collision. And you may know that a rear-end collision, okay, is going to have a lot less damage, okay, than a head-on collision. And somebody may say, well, why is that the case? If you have two cars that are going, let's say what we have here is 20 and 22 meters per second. If it's a rear-end collision, you can look at the velocities relative to each other. So relative to this car right here, the orange car, it appears like this blue car is moving at 2 meters per second. Because if you were to look at 20 meters per second and 22 meters per second, the difference between those two would be 2 meters per second. So the blue car would very slowly creep up to the orange car. So if the blue car were to hit the orange car, it would hit it at what appeared to be 2 meters per second. Now, if you were to look at from the blue car's perspective, it's kind of strange here. It looks like the orange car is actually moving backwards at 2 meters per second. So it looks like it has a negative velocity of 2 meters per second. So it's really important that you always judge motion based on where the observer is. So now we get to this idea of a head-on collision. So we have two cars, they're traveling 20 and 20. But if you've ever seen a head-on collision, they're very bad. And the reason why is whenever you take these two vectors and they're added together because of the nature of the relative motion between these two, from the blue car's perspective, it looks like the pink car is moving at 40 meters per second. And from the pink car's perspective, it looks like the blue car is moving at 40 meters per second. So whereas we had a 2 meter per second collision here, which is kind of break the bumper or something like that, here we have a head-on collision at 40 meters per second, which is well in excess of 100 miles per hour. So head-on collisions are always going to be more dangerous because of the idea of this relative velocity. Relative velocity is also useful when we're talking about planes. So planes have a top speed relative to still air. If there's no wind at all, a plane headed due south at 150 meters per second. That's how fast it moves relative to the still air. But there's wind whenever you're in a plane, and the wind can very much affect the motion of a plane. So it turns out that if you have a tailwind of 10 meters per second, that tailwind would come in and it would push the plane an additional 10 meters per second, giving it a velocity relative to the ground of 160 meters per second. Now, if instead of 10 meters per second as a tailwind, if you had a headwind, it would actually reduce the velocity of the plane because it would be pushing back against the plane, and it would reduce it to 140 meters per second. So you always have to be real careful and look at this from in terms of where you're viewing the motion from. This example, we have a car that is stuck behind a truck carrying bales of hay, and it's on a single lane highway. This is the truck is traveling at 45 miles per hour on a 70 mile per hour road. It's a little frustrating. You want to go ahead and try and pass the car. It says the law allows you to pass the truck using the other lane, but you have to pass the truck within 100 meters or risk hitting a construction crew up ahead. It says you hit 70 miles per hour just as you reach the back end of the truck. So right here, you're kind of going faster and faster. Right when you get to the truck, you're ready to pull out and around at 70 miles per hour. So now the question says, will you pass the 20-meter truck before hitting the construction crew 100 meters ahead? So there's kind of a lot going on here. The first thing we want to do is we want to determine the time that it's going to take for this car to pass the truck. So the first thing we want to do is we want to look at the velocity, the relative velocity between these two terms. So the first thing we want to say is we want to say that the velocity relative between those two things would be 70 minus 45. But of course that would be in miles per hour, and we don't want to do that. 25 miles per hour isn't going to work. So instead we convert it to meters per second, and when we do that, we get something along the order of 11.2 meters per second. So now we have the velocity of the blue car relative to the truck. We also know the distance that it has to travel during that time. During that time, it's got to travel a total distance of 20 meters. So what we can do is we can say, okay, well, if it's got to travel 20 meters and it's 11.2 meters per second, we can say that V equals delta D over delta T. Or in our case, we can say 11.2 equals 20 divided by delta T. We switch those things around. We say 20 divided by 11.2, and we get a number like 1.79 seconds. So the time is 1.79 seconds. So that's how long it takes this car right here to pass the truck. But remember, the car's not actually traveling at 11.2 meters per second. Instead, it's traveling at that 70 miles per hour, which when we convert that 70 miles per hour into meters per second is really 31.3 meters per second. Now, we have that 31.3 meters per second, and it's going to travel that full speed in the opposite lane for a total of 1.79 seconds. So we can do this equation again. V equals delta D over delta T, and we can get 31.3 equals delta D over 1.79. Now, when you take those two numbers and you multiply them together, you end up with something around 56 meters. Now, since 56 meters is less than the original 100 meters, it turns out that the driver is going to have about 44 meters of clearance between him and the construction crew. Example A2, and it says a Boeing 747 takes off at 7:04 from the airport in Houston and heads towards San Antonio. It says the plane experiences a 15 meter per second wind from Houston to San Antonio, and that same wind as it makes the return trip. So no matter what, the wind is always pointing this way at 15 meters per second. And so this question says, all right, assuming everything goes as planned, will the plane land in Houston on time or at the same time? And it says justify your answer using the clear method. So the first thing we want to do is we want to make up a hypothetical velocity for this plane. I'm going to say that the plane goes 200 meters per second. And I want to say that the plane, or the distance between these two, is, I'll just make something up. I'll say it's like 50,000 meters, which is incredibly small, so maybe we'll make it 500,000 meters. So now that we have this distance and we've got this hypothetical velocity, the first thing I want to do is I want to take a look at what would happen if the velocity was aiding us. So we would go 500,000 divided by the time would equal our velocity, but I want to add to this velocity our 15 meters per second. Our wind is going to aid us on the way there. And so we would have and we would switch these two numbers, multiply both sides by delta t, divide both sides by 215, and you would get 500,000 divided by 215 gives you 2,325 seconds. So we have 2,325 seconds it takes for a wind-aided trip. Now we switch it to our return trip, and our return trip says 500,000, but now instead of adding it, we're going to take away. We're going to say that's going to equal 285. When you flip these two and you solve for the time, you would get 500,000 divided by 280. This should be 185. You would get 500,000 divided by 185, and you would get something like 2,702 seconds. Well, when you add these two times together, you would get your total trip. So 2,702 plus 2,325 would give you a total time of about 5,027 seconds. Now, if you had a completely windless stationary trip both ways, you would have to travel 1,000 meters. You'd have to travel there, 1 million meters. You'd have to travel there and back. You would have a velocity of 200 meters per second the entire time. If you were to take and flip those numbers, you'd get 1,000,000 divided by 200, and you would get 5,000, which is pretty close to our number here, but it's not exact. So if you were trying to do this, remember the clear method is you need to state your conclusion, you need to provide evidence from the question, and you need to use some sort of reasoning. That reasoning could be mathematical, or it could be any sort of logical reasons in order to figure out what this particular question is. So you need to be able to write your own clear method paragraph based on what we discussed. This is example A3. You should be able to entirely on your own determine that the change in time for the man as he runs along the people mover as opposed to just sitting there, he would save about 75 seconds. So you should be able to do that all on your own. So now if we take a look at the PBL that we did, it says that time can't be retroactively measured. And we decided to use this equation, this formula that was provided to you by the police officers and the insurance company. So you had this idea of VI is equal to the square root of VF squared minus 2AD. Well, it turns out that this comes from the fact that we have these right here. We have our two original equations. These are our two original equations that are determined by the slope of a velocity versus time graph and the area of a velocity versus time graph. Well, it turns out that sometimes you can't measure time. Like whenever you're looking at something after the fact, you don't have a stopwatch, something along those lines. So what we want to do is we want to solve this equation right here for delta t. And that's actually what we do right here. If you kind of take a look, we take both sides, you multiply them by delta t, crosses out there, and what we're left with is a delta t equals vf minus vi. You divide both sides by a, and you get this term right here is equal to delta t. At that point, you can plug that in to there. When you plug it in, you get this mess right here where you have delta d and or 1/2 vf plus vi, and then you have to multiply it by this term, and that's going to equal the original 1/2 or 2a delta d. And so you have to do some rearranging. Once you do that, you end up multiplying both sides by 2a. The reason why you multiply both sides by 2a is because you want to eliminate the half term and you want to eliminate the a term. In doing so, you move these terms over to the other side. So now you have this 2a equals vf plus vi times vf minus vi. Now, you've probably learned this in math class already, but there's a technique called foiling. Whenever you have these two expressions, you can result in a polynomial. So you do is you take the first terms and you multiply them together. So you would get vf times vf would be vf squared. You would take vi, and then the next term is you would do the outer ones. So the outer ones is vf times negative vi, so you would get negative vi vf. Then the next thing you do is you multiply the inner terms. You would get a positive vi vf, And then the last terms you would do is you multiply these last ones and you would get minus vi squared, because vi times negative vi is negative vi squared. Well, if you look, these two terms are actually equivalent. Negative vi vf, positive vi vf. Those terms can cancel out, and we're left with vf squared minus vi squared. Now, we rearrange by dividing both sides by 2d, and what we're left with is this right here. This is our fourth kinematics motion equation. It is the only equation that does not have delta t, and so if you don't have time, can't measure time, not interested in time, this is the equation that you would use. So we have the equation is a equals vf squared minus vi squared divided by 2 delta d. Now, some physics books actually like a different version of this formula. They actually like the version of the formula vf squared equals vi squared plus 2ad. Now, both of these are valid algebraic rearrangements of the same equation. We're not going to go over this stuff. You should know this stuff already by heart. We haven't introduced any new variables, just a new equation. This says a driver sees a cat in the middle of the road, 15 meters ahead, and immediately slams on the brakes. The driver has a known reaction time of 0.34 and was initially traveling at 12 meters per second with a maximum deceleration of 5 meters per second. It says, will the driver stop in time? So the first thing we need to do is we kind of got to draw this out. We know that the driver is going to try and make it right here. We know there's going to be a constant velocity part, and that constant velocity part is due to the reaction time, the fact that he hasn't applied the brakes. And then we have a deceleration part. So this is the part where he's slowing down. And we want to know if he's going to hit the cat. Down. Okay, so now we take a look at this and we say, okay, what is our given information for constant velocity? Well, we know that he was initially traveling at 12 meters per second, and we know that his reaction time was 0.34 seconds. We do know that this is constant velocity, so we know our equation is going to be v equals delta d over delta t, or 12 equals delta d divided by 0.34. We multiply both sides by 0.34, and when we do that, we get delta d is 12 times 0.034, or 4.08 meters. Now, that's the displacement while he's traveling at a constant velocity. So you may say, oh, well, of course he doesn't hit the cat. The cat's 15 meters ahead. Remember, he still hasn't even applied the brake yet. Now we have to do the part where he slows down. And when he slows down, we have the initial velocity is 12 meters per second. We know the final velocity is going to be stop. We know that the acceleration is a negative 5 meters per second. Now, the reason why we know it's a negative is because it says it decelerates at 5 meters per second squared. And then we want to know the distance that it travels as well. So we say, okay, A equals Vf squared minus Vi squared divided by 2 delta D. We have negative 5 equals 0 squared minus 12 squared divided by 2 delta D. The first thing that we're going to do is we're going to go ahead and say 0 squared is 0, and negative 12 squared, or excuse me, this is 12 squared and then subtract. So this ends up being negative 5 equals negative 144 divided by 2 delta D. So you kind of rearrange this a little bit. The first thing we want to do is we want to switch this 5 and this D term. So we end up getting delta D equals negative 144 divided by negative 10. The negative signs are going to go ahead and cancel out. And so 144 divided by 10 is 14.4 meters. Now if you look, this is the distance that it decelerated at. So we have two distances that we need to add together to get the total distance. So we have 4.08 plus 14.4, and that's 18.48 meters. So unfortunately the cat is going to be hit in this particular case. But the reason why is not because of the car, it's because of the driver. If the driver was paying more attention and had a better reaction time, there was sufficient distance to stop, except for the fact that the driver wasn't paying attention. Okay, this is the next example. It says you have what is the maximum height of a baton thrown upward at 20 meters per second. Uh, so we throw it up in the air. We want to know what is the maximum height. Now remember, we said there's some key information that's hidden in these vertical questions quite a bit. So we know the only thing that's outwardly stated is that the initial velocity is a positive 20 meters per second. We know that because it's thrown up in the air. Now remember, anytime you have a vertical question, if that baton has been released, it is under the influence of gravity, and that means the acceleration is negative 9.8 meters per second squared. Got to be negative. Okay, gravity does not all of a sudden switch because you threw a ball up. Negative 9.8 meters per second squared. You also know at the maximum height, that ball goes up, 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 slows down, it comes to a stop. At its highest point, it comes to a stop, indicating its final velocity is 0. And you are trying to solve for the displacement. So you will use the equation A equals Vf squared minus Vi squared divided by 2 delta D. Make sure you plug your numbers in, and after you plug your numbers in, you should be able to tell your teacher what the correct answer is. Example A3, you should be able to work out entirely on your own. It says a car accelerates from rest to 85 meters per second in 400 meters. What is the acceleration of the car? You should be able to get 9.03 meters per second squared, and you should be able to do it entirely on your own, and you should be able to reproduce something like that on a quiz.